Hi, I'm not sure whether you can hear me, but I've made a bit of progress, a bit surprisingly. I didn't think I was going to make any after what I found. The problem is this. If we take the... Sorry, I'm having a bit of trouble with the light here. If we take the Aronoff picture, what we've got is this, where we essentially have a particle interacting with itself. And Aronoff argues that we can essentially zero. Sorry, I'm still having trouble with this. That we can essentially zero every region outside of the light cones. Now, the problem is, if we do that, we have a near field here and a near field here and a far field here and a far field here. Now, that essentially scuppers that idea because we just can't compare these things. We can't renormalize it in any way. We're just chopping off bits of the wave function. And so then you go, okay, let's try and compactify it like, so sorry, I've got to work out some peculiar geometry here. Let's try and compactify it in a kind of conformal manner, like a Penrose diagram. Now at least we've got near field to near field. So we have our waves going like that, then kind of reconverging in. And then we have our down movers moving in like the other way. And basically, this won't work either because everything's going to cancel each other out and we're just going to land up with nothing. And so then you go, okay, well, there's not much left. We've got to do something like this, but we've got to introduce some chirality into it. So let's just think logically what we're trying to do here. We're trying to find a fixed point for a loop amplitude. And so this isn't going to be an easy problem. But at the same time, if we can find a really nice solution for this loop amplitude, then we have solved a huge problem because the whole system will be in thermal equilibrium. And we have no requirement for inflation. The only remnants of any thermal instabilities or differences are going to be tiny, and they're just going to be a result of essentially the quantum numbers of the original excitation. So let's be clear what we're doing here. Even though we're dealing with one excitation here, it seems useful to write it as two, A and B. Now, B is actually A just forwards in time. But at some time, not now, I've got to check all the statistics, and there are a few ways that you can arrange things. So, all right, now here's the thing. In my ramblings on the notes to the first part, it became apparent that we had to get rid of a lot of positrons, and the easiest way was to hide them across a event horizon, and the logic of the first episode was okay, but it was relying on this near field far field incompatibility, and so I thought I wasn't going to be able to solve this because it just looked so horrible. But then I thought, well, let's draw this midline, because that's the line where we know what's going on. We essentially know that B has propagated all the way to there and has met A, and then we've just got this essentially event horizon there. Now, this looks quite different from the Penrose topology, but it's similar. It's on the same diagram, but it's just regarding it in a different way. And so here we're seeing A, and we're hoping fermionic partner of itself, B, which is itself A. So we've got Alice and Bob, but it's actually Alice and Bob and Bob, or they're indistinguishable. So we're going to expect to be able to swap them and change a sign. And so what we can do is say, okay, well, we know that the up movers are going to hit the event horizon, and the down movers are going to hit the event horizon. We don't really care too much about the interference pattern because that's what we're trying to calculate. And so we just really want them just to propagate on the same space and not interfere at all. We just want them to propagate from A to B and from B to A, not do anything, and then we can start to build up something from this. So what we can do is say, okay, from the point of view of A up here, we can have a unitary U there. And from the perspective of B moving down there in that direction, we can have, it can meet a unitary. So this is on this side for this things going that way. And for this side, they can have another different unitary V. That essentially what we can do is do a diffeomorphism of the rays. So we just, so, all right, so this U consists of basically just gauge transforms. And so we can shuffle things however we want, but we can only do it once. We just pick the shuffling operation. So we pick any old diffeo, let's say I don't want to write any of the letters, F maps S5 to S5. And then what we've, this is all inverted. Oh, well, it's good for the topic. It's all flipped anyway. So F maps S5 to S5. And then We've also got other various gauge transforms, but there's one that we really, 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 really want to do, because the problem is that as far as the A is concerned, it's propagating in the space of positive curvature. And so we can only admit normal particles in there. Now, there are even more caveats. So in here we have like the standard model, or whatever, chiral gauge theory you want. And up here we have a SUSY model. Now, this is as far as these waves are concerned. So for the up movers. Now, the reason we want to do this is many reasons, actually. First of all, this can get rid of all of our electrons. So, all of our positrons, rather. Because what happens is, suppose we've got a vacuum decay, and we can just use, the nice thing about this is it is string theory, but we're kind of doing vertex operators on a brane. So we're just dealing with poles on a Riemann surface. Boom, boom. There and there, and in fact, it's just a quadratic singularity, which fits because that's just giving us a branch point that looks like this. So we can imagine that we've got a photon coming in here, and it's decaying into an electron here, which has positive time. And then we have an electron here, a positron rather, E minus, and this has negative energy. So it's moving backwards in time. So on the Riemann surface, this is a branch point. And so this basically is what allows us to model interactions using Riemann surfaces, because we can trace out the various realities within the monodromy group. So if we have and so using that way, we can start to represent superpositional states using a kind of wiggly way, that your typical Riemann surface has got like well, in this case, it's simpler. We've just got a branch cut here, one branch cut. So we've essentially just going round up and down one story. So it's like we got one, so we're just looping around, going up, down, up, down. So we've basically got two states of reality that we can encode. And now what's really nice is the Spicer dynamics, and this is where really the whole thing falls apart, and we can just start to take the dynamics to pieces, because so we have a little bit of choice. We've got a diffeo, we've got a gauge transformation of some type of in U1, the gauge group of the system to itself. So we've basically just got a couple of automorphisms, and that's basically all we can have, because it's an automorphic form. We're just dealing with the interactions of a system with itself. Now, And so, and the fixed points are going to be our loop amplitudes. And so what we want to do is now start to decode the dynamics of this surface. Okay, so what we've got here is that we need to get rid of this. So, but the thing is that this branch point is has an event horizon associated with it, so that every branch point has one of these surfaces. So I better write down the equations now. So just to cut to the chase, what we do is this. It looks like you want to just do something obvious to it, but you can't. It just looks like U and V are these uh, Hermitian operators and unitary operators, rather. And we've got a bit of choice in them. And you guys want to say, oh, well, remove one of the degrees of freedom and move it over there. But we can't really do that, because what we're doing is they're not what V is doing is it's taking the far field and it's compressing it back down onto the near field like that. And the other thing is okay, so we've got positive curvature in here, negative curvature in here. So in here, we can't get standard model particles. We only have SUSY particles. So in other words, if we have a photon in here, now, but photons are meant to live on event horizon, so this is in a mixed state. And so this mixed state photino has to map onto a mixed state, sorry, photino here. And then photons, possibly photinos, in their pure states, and every pure state only lives on one of these event horizons. And so what are these event horizons? Well, we've already got the formula for that, because all we need to do is derive the Higgs field from this equation. So we're just, it's like, yeah, we find the operators to make this fermionic if we can, and if it's not, it's bosonic, but my guess is we'll end up with a fermionic solution. But let's just work through just see what falls out anyway. So so we've got this product now where we're comparing UA with UV, and this is our Higgs field. So and this is, so we embed this as the phi naught. So we're basically going and embedding like this into SU2. And now this is where it was this zero that really forced a lot of the theory, because it's not zero in the standard model, although it's gauged out. And so in the standard model, the Higgs is a scalar doublet, but here it's a scalar singlet with a trivial doublet partner, and so this results in us being able to carry for an event horizon to carry hypercharge and isospin, but not charge. And so this is what led me to actually find these kind of maze-like permutations, because we need these to rotate to perform the supersymmetry operations. So one is doing a supersymmetry operation, and that supersymmetry, that's going supersymmetry down, and this is going supersymmetry up. So we can just see that supersymmetry is essentially just a binary quantum number. So it's just a quantum number or a +1 and -1. And then so it's a spin one. Uh, uh, oh, yeah, or spin. What is it? Okay, so but the point is this is our Higgs, and this is where this is so the real part is our vacuum energy, and so that is equal to the curvature. And we can actually write down quite a lot of the Riemann tensor terms straight off. I haven't even done that yet because I'm just trying to see whether the basic ideas work. Because if they don't work, there's just no point pushing this forwards. But it does seem quite promising. And so now where we have the real part of phi 0 equals 0, that defines an event horizon. And we can see from this logic that an event horizon occurs at every interaction vertex because or starts at every interaction vertex, and that essentially this where these where the event horizons are, this is the boundaries of the fundamental domains for the Riemann surface. So what we've done is, even though this is some probably horrible non-oriented or potentially non-oriented surface, we can split it up into fundamental domains. So we take our manifold and, all right, I've called that delta, but let's just factor it out by our automorphism group. But the point is this is fixed by the quantum numbers. So we've got a map uh, uh, H maps N, and we can just call it N because we can just encode the Gödel number. We can Gödelize the quantum numbers if we want, or we can treat it as some higher dimensional space. But we can just treat this as a map from the natural numbers to the manifold, to the Riemann surface factored out by its automorphism group, and we can basically cut it along all of these singular boundaries, and it just falls nicely into manifolds, even though the thing is a pretty horrendous orbifold. And so basically, once we've got that, then we can just do all the Green's functions and everything like that on it. Everything just falls out, and we'll find that gives us all our quasi-conformal stuff. Obviously, the formulas are still very intricate, but we've made contact with the fundamental reasoning as to why we need SUSY in order to prevent a collapsing universe, because we need for photons to interfere with photinos, and this just resolves a whole lot of problems. And now maybe the final point is this is about the vacuum energy. What's going on here? So we do the same diagram, and we think about it from the point of view of A. And what is happening is that here, imagine we're borrowing vacuum energy. And as you know, the vacuum hates to lend energy, but it will always hit this point where it says, right, time to pay it back. So this is the repay mechanism. We're having to repay stuff. Now, if we just look at it like this we've borrowed and we've repaid. But now if we look at it from the point of view of B is at the same time going down here, borrowing. And then here, repay. So it's like here, and the exact amounts of energy borrowed, and then at the event horizon here, everything is equal. I mean, this is on maximum loan. This is like crunch time. And peculiarly, it's also crunch time for B. So we've got a consistent view of reality that this is crunch time. And here, the arrows are all going this way. So we've got a situation where A is robbing B and B is robbing A for their energy, but A and B are the same thing. So A is stealing the energy from its time reversed self and then repaying it and recycling. So this is how we can get this vanishingly small cosmological constant, because the entire system is self-contained. It doesn't interfere with anything else at all. If we wanted, we could put this, this looks like a kind of, what is it, ZTB, a fluctuation of the width, but because this is there's no field influence on anything out here at all. So essentially, we don't need to be borrowing any vacuum energy to find the actual loop amplitude, because it's all being borrowed from itself in the collapsing phase. And that's what it means to be a zero entropic system. So this thing, remember, is in the same place. So the scales that we've put here are essentially irrelevant. This is a scale independent picture, because we have a system that's living in its own little internal world that might occasionally run into a branch point and find that it's actually got a decision to make. But they're always going to be binary decisions, because the Riemann surface has only got second order poles, and that turns up everywhere in the 1/r squared. So, you know, when we're looking at dimensions, it's just like, how many dimensions does a sphere spread out into, which is why the effective potential for gravity is such an intriguing formula. But so basically that's it. This gives the cycle, this gives what everyone would look for, which is the essentially Galois correspondence, which allows us to build an algebraic manifold from a group. And we've done it. We've got the event horizons, and we can be doing our Green's functions on there, and so we can get potentials, everything. And we essentially have the most important one, which is a dilatation, which is probably going to give us, you know, it's telling us it's conformal on this where it's zero, and it's quasi-conformal where it isn't, and so that's a dilatation, and which is right where I started, strangely enough. So it really does seem like it's a theory falling backwards in time. But from a mathematical point of view, it's almost like the field details aren't that interesting. We can stick in any chiral groups we want here, as long as we've got a supersymmetry sector and it's chiral, because if we don't have the chirality, we're not going to be able to make this system uh, interfere with itself without just destructively interfering with itself without the appearance of making any work at all. But at least this gives a practical model for computing. And in fact, it's just an extraordinarily fast quantum computer that's working on qubits. We can just see it here. The Riemann surface is the Riemann surface of a binary quantum computer with fundamentally classical bits storing whether you what sheet of that particular Riemann surface you're on at that place. So the details are fundamentally binary. And so it's physics is extraordinarily beautiful, really, that it uses such a intricate method to avoid the loop amplitudes just cancelling out to nothing. This is a case where we do want there to be something, but we don't want it to be so enormous that we can't actually compute it. And the interesting thing about this is that it's really not hard to compute as long as we've got the propagators and we've got the gauge group and we put it into Hermitian form. That's the really important thing. And then we get all the interaction vertices sorted. Then essentially this just gives us loads and loads of models to play around with and see what they look like. And but qualitatively it's pretty easy to see that they look very similar at the same energy levels, and they're holographic, and they're essentially little perpetual motion machines that do no work, no overall, but give the appearance of doing work because of the no signaling theorem. Now that gives the last interesting patch, that if you think that we are going to have regions within this, so if you think that the actual universe is actually going to be, patches of event horizons around here, so we've got a kind of, and then we're going to have reverse patches here. So this is positive, mainly positive curvature. This is mainly negative curvature. And so where you've got mainly positive curvature, you're going to get negative curvature rather. So we got positive curvature here, we can exist here. We can't exist in these patches here, but there are patches with standard model physics here. And so it is, and so if you're in a negative universe, you could actually fall into another event horizon that is a different positive curvature universe and experience time going forwards, but within a collapsing universe. And so that's just a little peculiar thing, really. And it might be that if you're in that collapsing phase, you'd get a really good, amazing view of what was going on. And perhaps that's where why all this information is going backwards in time, because it's essentially all the information is here already, and we're just like, as more of the picture reveals itself, then it becomes very clear what's going on. But then again, that's also not a great sign, because our measurement of the cosmological constant is extremely small, and that means that if you can imagine that near A in this bit, there's, well, I suppose the thing is that cosmological, and this is the thing, that the cosmological constant is always going to be fairly small. But we have to be very careful about looking at the effect of this and the identification of rays between well, we actually have two of those, don't we? So um, we have one going up in this direction. All right, well, they're already included in the U and V. So each of those U and Vs contains a diffeo S5 to S5 and an automorphism of the gauge group to itself. And they can be different. So we can create extraordinarily long uncorrelated cycles. And now that's from the point of view of information theory, that's really, really important, because what if you just do the same thing every time, Bell's theorem fails, or rather you don't get any advantage from entanglement, because you've become a highly correlated part of the system, and you're trying to pick out correlations, and they've just become overwhelmed by your correlation with yourself, and so the actual subtle entanglement has gone somewhere else. And so basically, in this case, we're needing to create an apparent lack of correlation in order to create the strong mixing, the fast scrambling on event horizons. So the more imaginative the diffeomorphisms can be made. Well, the diffeos, in fact, I think we can. Oh, because they're all taking their place. There's only one diffeo. That's interesting, because the yeah, there has to only be one diffeo, but I think there can be two gauge transforms. All this has to be checked, obviously. So, but you can basically be very imaginative. Yeah, it doesn't look like there's much gauge freedom in the diffeo, so we might as well just glue ray to ray. Although, but no, it will scramble things up a bit, and we want to scramble things. But we essentially have to give it some kind of computable scramble. And basically, we're just trying to get the whole system naturally to be permuting its monodromy group, so that the entanglement can spread rapidly over the system, because that's what it's trying to do. It's essentially trying to dissipate entanglement. And then but I think that about wraps it up for now, and probably I'll log on the next time I find a dire problem that is causing the whole system to look like it's going to collapse into a mess. But I think this might actually hold together, because it's kind of made contact with the Galois theory, algebraic geometry, and all of the lovely Riemann surface work. So and we've got deterministic equations. So that means that essentially, as far as we're concerned with this loop amplitude technique, we're not immediately after the amplitude. So but what we've got is the Higgs field, and the behavior of this Higgs field can tell us a lot about the rest. Well, we can basically, once we've got the monodromy group, we can start to do dynamics on it. And that was really Einstein's dream, to establish a connection between the natural numbers and Riemann surfaces. So I guess that's almost there. Really, the final thing will just be to tie it all up with the Beltrami equation or whatever variant of it is needed to solve the dilation equations. But if we're doing it, well, it's basically a 26-dimensional Beltrami equation or something, but it's split up into 13. But I don't know. But Noel thought it worked. And so, but I don't know how I jumped. I basically jumped in here without knowing all of this stuff. So a very peculiar way for it all to unwind backwards in time. But so I suppose I ought to just start thinking about it and saying, hey, this is how it all works to myself earlier in time. And then maybe the message will get through, because it seems to have so far. Anyway, I guess that's it. And thank you for following me. And I'm sorry if this is all upside down, mirror reflected, but that is the theme. So enjoy yourselves. Bye.